Section 2.6, Rational Functions. So within this section, we want to be able to analyze and graph rational functions. Just like the last section with polynomial functions, you started with looking at the polynomial itself, analyzing that polynomial by finding all of the intercepts and leading coefficient and degree, and then using that information to graph it. We're going to do the same thing in this section. We're going to start by looking at the rational function. We're going to analyze it. And when I say analyze, this time we're going to be identifying domain, still going to be identifying x and y intercepts. We're going to use the domain to help us find vertical asymptotes. We're going to find horizontal and slant asymptotes. A more generic word for slant would be oblique asymptotes. Anything that's not vertical or horizontal is an oblique asymptote. And holes. So there's going to be a lot more information that we need to find when we're looking at a rational function than a polynomial function. But good news is with practice, it becomes second nature. Now, first off with that keyword domain. When we were talking about polynomial functions, we never actually wasted time answering that question. We technically should always answer that question, no matter what function you're looking at. You should always pay attention to the domain, but when it comes to polynomial functions, there was no need to. If you recall from Chapter 1, polynomial functions have a domain of all real numbers. Domain is what x values you are allowed to use in the function, and in a polynomial, there are no restrictions. You can plug in any x value you want. You will always get a y value that x value corresponds to. With rational functions, in other words fractions, that's not always the case. So because that's not the case, it's crucially important that for every rational function you're given, you start by identifying the domain. Because remember, a rational function is a fraction. Rational, root word ratio, which means fraction. We have a numerator and a denominator, top over the bottom, and when it comes to domain, the only restriction we have is when the denominator equals 0. So the domain of a rational function is all real numbers. Denominator cannot equal 0. We talked about this way back in Chapter 1. But those points at which the denominator equals 0, in Algebra 2 you refer to those as restrictions, domain restrictions, values which are not allowed to be used. In the context of graphing, we give them a slightly different name. We call them discontinuities, because if those are not within the domain, then they do not have corresponding y values, which means the graph can approach those coordinates, but they can never actually reach those coordinates. So at some given x values, there is no y value. So there may be a wall in the way. You may have the graph on the right side of that x value and on the left side of that x value, but you don't have any graph at that x value. So we have a point where the graph is not continuous, a discontinuity. Now, those discontinuities, those domain restrictions, can be broken into two different categories. They can be holes in the graph, or they can be vertical asymptotes. Now, let's start by talking about a hole. A hole is a point on the graph, where the graph is continuous everywhere except for that point, but at that point there's just basically a gap. There's a hole. The graph just simply does not exist at that single coordinate. So we have a nice, smooth, continuous graph, except for at a single coordinate there's a hole. Now here's an example of a graph that has a hole in it. X squared minus 1 over x plus 1. Now I do not expect it to be obvious just by looking at the equation that we have a hole, but we start by looking at the domain. Remember, every single rational function we start with the question of domain. Domain is anytime the bottom equals 0. If I look at the bottom, x plus 1, set it equal to 0, x equals -1. So the domain is all real numbers except x cannot equal -1. We have a single domain restriction. Now at this point I still don't know if that domain restriction is a hole or a vertical asymptote. The way we determine that is we look at the top. Notice the top, x squared minus 1, difference of squares, can be factored into x plus 1, x minus 1. And then when I look from top to bottom, I see something in common. X plus 1 appears on both the top and the bottom. Anytime I have a fraction with something in common between the top and the bottom, it can be canceled out and simplified down to just x minus 1. So let's think about what we did. We took a fraction, we simplified it, and we have our simplified form of that fraction. Just like if I had 2/4, simplifies down to 1/2. The simplified fraction is equivalent to the original fraction. So if I asked you, hey, what does this graph look like? Really, I could just look at this graph. Well, this is much easier. This is a line, y equals x minus 1. We have a y-intercept at -1, a slope of 1, so we have our line y equals x minus 1. But we have an issue. There was a domain restriction on the original problem. Therefore, that domain restriction still applies to the x minus 1. At x equals -1, there's supposed to be a gap in the graph. The domain should not exist at x equals -1. Therefore, on the graph, when x equals -1, we should have a hole. That hole is not at anywhere at x equals -1. It is a point on the graph at x equals -1. So to figure out the y value, obviously after graphing it, I know that the y value is -2. But really, we can just take that -1, plug it in. Anytime you want to find a point on the graph, take the x value, plug it in, get the y value. But if I plug it in here, -1 plus 1 is 0. -1 squared minus 1 is 0. If I plug -1 into the original function, I get 0 divided by 0. A, I'm not allowed to divide by 0, and B, 0 over 0 makes absolutely no sense. But if I plug it into the simplified version, notice -1 minus 1 is -2. So we have a hole at the coordinate -1, -2. We knew it was a hole not by the graph, but the fact that it canceled. If it cancels, it's a hole. That's how we know whether it's a hole or an asymptote. Find your domain restriction, look to see if that domain restriction can cancel out. If the factor cancels, it's a hole. Find the location of that hole by plugging your domain restriction into the simplified form of the function. It won't work in the original function, so if you mistakenly plug it into the original function, you'll very quickly find it's not going to work. Plug into the simplified version to get the y value. So we have a factor that cancels, it's a hole, so our hole is at -1, plug it in, -2. Now an asymptote, on the other hand, remember an asymptote is an invisible line that the graph approaches. We have vertical asymptotes, we have horizontal asymptotes, and we have slant or oblique asymptotes. Again, like I said before, an oblique asymptote is any asymptote that's not vertical or horizontal. In this course, we're only going to be looking at slanted oblique asymptotes, in other words, asymptotes that are just lines, that are non-vertical, non-horizontal lines, but there's actually no rule against an asymptote being any shape it wants to be. You can have a parabolic asymptote, you can have an asymptote that's a nice, pretty S-curve, you can have pretty much any shape that you want. In general, those are referred to as oblique asymptotes. But notice the definition. I said the invisible line that the graph approaches. You may be accustomed to the definition that it's an invisible line the graph approaches but never crosses. That is not necessarily true. Vertical asymptotes, which are discontinuities, I agree. Vertical asymptotes cannot be crossed. They are approached, they are never crossed. Horizontal and slant asymptotes are not discontinuities. You can have continuity over a horizontal or slant asymptote. There is no restriction to crossing horizontal and slant asymptotes. Only vertical asymptotes are the ones that cannot be crossed. Now we're going to talk about horizontal and slant asymptotes a little bit more a little bit later. Right now we're going to stick to just vertical asymptotes. So let's pull this function up again, but notice this time it's upside down. We can still factor it out the same way, and that helps us to identify our domain. This time, instead of the domain only having one restriction, this time the domain has two restrictions, at -1 and +1. Now it's possible both of these might represent holes. Maybe they both represent vertical asymptotes. Maybe there's one hole and one vertical asymptote. If I look top to bottom, once again, I still see a common factor, x plus 1. Therefore, the solution, x equals -1, which canceled out, must be a hole. So x equals -1 is a hole because its factor canceled out. But notice x minus 1 did not cancel out. Because x minus 1 did not cancel out, I know that x equals 1 is not a hole, it's an asymptote. If it cancels, it's a hole. If it doesn't cancel, it's an asymptote. So if I go to graph this one, again, I graph the simplified version, not the unsimplified version. 1 over x minus 1, if you recall, 1 over x is our reciprocal function. I remember the reciprocal function. That's the one that has the vertical asymptote at 0, at x equals 0, and the horizontal asymptote at y equals 0, and then it appeared in the first and the third quadrants. It appeared in the first and the third quadrants as our can't touch this graph. But remember, this one is shifted to the right one, so the vertical asymptote's not at x equals 0, it's at x equals 1, which is exactly what we just said. we have a domain restriction at -1 and +1. -1 is a whole because it cancels. X equals +1 is my vertical asymptote. So I could get that vertical asymptote either by using my transformation techniques from chapter 1 or my discontinuity domain restriction techniques that I'm currently talking about in chapter 2. So I have a vertical asymptote at x equals 1. We already established in chapter 1 that there's a horizontal asymptote. We're going to talk about a little later another way to determine that there's a horizontal asymptote. And again, it was just the hammer time, the can't touch this graph. But of course, let's not forget we did have a hole at -1. To figure out the exact location of that hole, take -1, plug it into the simplified version. -1 minus 1 is -2. So in other words, -1 is my x value, -1/2 is my y value. So I have a hole in the graph at -1, -1/2. Again, holes are what cancels. Factors that don't cancel are vertical asymptotes. So let's summarize and do an example at the same time. We're going to analyze this function by stating the domain first. We always start with the domain. Then we're going to identify any holes, any vertical asymptotes, and while we're at it, let's go ahead and throw in intercepts. Always start by factoring everything out. The best way to figure out what the domain is, as well as to see what's in common between top and bottom, is in its factored form. So let's factor out the top, factor out the bottom, and analyze from there. Once you've factored everything out, you can identify your domain by looking on the bottom. Roots on the bottom represent your domain. I don't care about the top at all for the domain. Once you've analyzed those roots on the bottom, once you've found those roots on the bottom, you can classify them as holes or vertical asymptotes. Remember, holes are the ones that cancel. Vertical asymptotes are the ones that don't cancel. But be careful, it has to be on the bottom. The top does not tell me anything about vertical asymptotes. It's only a vertical asymptote if it doesn't cancel and it's left on the bottom. So what if it's a root that's left on the top? Well, we've actually already discovered that. If we look back to that first example, remember x plus 1 canceled, but x minus 1 did not. X minus 1 was a factor that remained on the top. Notice at x equals 1, its root. At x equals 1, we have a x-intercept. If the root remains on the bottom, we have a vertical asymptote. If the root remains on the top, we have an x-intercept. So again, factor everything out. Domain restrictions are what you have on the bottom. Anything that cancels is a hole. Anything that doesn't cancel, if it's on the bottom, it's a vertical asymptote. If it's on the top, it's an x-intercept. So let's look at this one. Why don't you go ahead and give this a try, see what you can figure out, and then hit play when you're ready. Alright, so x squared minus 4 is the only piece that can be factored out, so we'll factor it out as x plus 2, x minus 2. Therefore, I can identify my domain before I start canceling anything out. Identify your domain, all real numbers except x cannot equal -2 or +2. So there's my domain. Now remember, positive and -2, those represent either holes or asymptotes. Maybe they're both holes, maybe they're both asymptotes, maybe it's one of each. So if I look to see if anything cancels, I see that the x minus 2 cancels, leaving 1 over x plus 2 as my simplified form. Since the x minus 2 canceled, that means x equals 2 is where my hole is located. But remember, it's not just x equals 2, a hole is a coordinate. So x is the 2 is the x value. Plug that 2 into the simplified form to figure out the y value. 1 over 2 plus 2 is 1 over 4. I have a hole at the coordinate 2, 1/4. Now x plus 2 was left behind. It's on the bottom. Therefore, I have a vertical asymptote at -2. Notice there were no remaining roots on the top. 1 does not count as a root. 1 is a constant value. It can't ever equal 0. Therefore, it's not a root. So there are no x-intercepts. This graph will not have any x-intercepts. Now, y-intercept didn't talk about the y-intercept, but we know how to find a y-intercept. Just plug in 0 for x. If I plug in 0 for x into the original function, I get -2 over -4, which is 1/2. If I plug 0 in for x into the simplified function, I get the same thing, 1/2. It doesn't matter where you find the y-intercept, either one will work. But again, let's also remind ourselves, how do you find a y-intercept for polynomials? We just look at the constant term. Rational functions, same technique. We just have two constant terms. -2, -4, it's the ratio of the constant terms. So 0, 1/2 is my y-intercept. Alright, here's another one. Go ahead and give this one a try. Hit play when you're ready. Alright, so we're going to identify everything just like we did before. When we factor everything out, let's start with the top. Factors of -6 that add to -1. Well, that's just going to be +2 and -3. +2 minus 3 is -1. +2 times -3 is -6. On the bottom, we'll do the same thing. We'll look for factors of -2 that add to +1. Well, that's going to be +2 and -1. So we have our domain restrictions at -2 and +1. So domain all real numbers, x cannot equal -2 or +1. I see that the x plus 2 cancels, leaving x minus 3 over x minus 1. Since x plus 2 cancel, that means I have a hole at x equals -2. Its y-coordinate can be found by plugging in -2 into the simplified version. -2 minus 3 is -5. -2 minus 1 is -3. -5 over -3 is 5/3. The factor that remained on the bottom was x minus 1, so x equals 1 is my vertical asymptote, while x equals 3 remains on the top, therefore it's my x-intercept. Y-intercept is simply the ratio of the constant terms, whether it be -6 to -2 or -3 to -1, either way, 0, 3. Alright, so we've got most everything under our belt. We just have a couple more things to talk about, the horizontal and slant asymptotes. We find vertical asymptotes based on domain restrictions. Horizontal and slant asymptotes are not found based on domain. They have nothing to do with the domain. Now, remember, we've talked about horizontal asymptotes. This is a vertical asymptote. This is a horizontal asymptote. So remember, horizontal asymptotes are horizontal, therefore they are y equals a number. That also justifies why they're not domain restrictions. Domain restrictions are x values. Horizontal asymptotes are y values. A slant asymptote is really just a horizontal line that's not horizontal, it's just slanted, so it's still y equals some function of x. It's just an equation of a line that represents an asymptote. So still, slant and horizontal asymptotes are y equals functions, not x equals. That's again why they are not domain restrictions. They have nothing to do with the domain. They are y equals, not x equals. So remember, horizontal asymptotes are horizontal. Slant asymptotes are slanted. Notice it's really just the same graph. It's just taking the horizontal asymptote and tilting it a little bit. And for this reason, they are never together. You can either have a horizontal asymptote or a slant asymptote. Basically, a horizontal asymptote is just a slant asymptote with a slope of 0. So they are found the same way. They represent the same thing. They cannot appear together. You can have one or the other, never both. You can have vertical with both. Here's a vertical with a horizontal. Here's a vertical with a slant. But you can't have a vertical, a horizontal, and a slant at the same time. It's just not possible. So here's the rule. Given some rational function where ax to the m is the leading term on top, bx to the n is the leading term on the bottom. It really doesn't matter what else is going on in that those separate polynomial functions. I can write whatever I want as long as this is the leading term on the top and this is the leading term on the bottom. We find horizontal and slant based on the relative degrees of the top and the bottom. So let's start with the first one. N is bigger than m. So if n is bigger than m, we would call this a bottom-heavy function. So think of the top function and the bottom function as involved in an epic battle. The top is constantly trying to pull the graph up to infinity. The bottom is trying to pull the graph down to 0. If it's bottom heavy, then the bottom is winning. The bottom is eventually going to win. No matter how hard the top tries, the bottom is going to win. So if it's bottom heavy, we end up having a horizontal asymptote at y equals 0 because the bottom is pulling the graph down to 0. Now if there's a horizontal asymptote at y equals 0, then that means there is not going to be a slant asymptote. So a bottom heavy function, anytime you see a bottom heavy function, you can automatically say horizontal asymptote at y equals 0, slant asymptote does not exist. There isn't one. Now, on the other hand, if n is smaller, m is heavier, we have a top-heavy function. So in this case, the bottom loses, the top wins, the graph gets pulled up, up, up to infinity, but it's not going to level out at any point. It's just going to keep getting bigger and bigger and bigger, so it's not going to be a horizontal asymptote, it's going to be a slant asymptote. Now, there is no rule of thumb for the slant asymptote. You can't just say slant asymptote equals this. You're going to find that slant asymptote by doing synthetic division. So if it's top heavy, that means you have a slant asymptote. You find that slant asymptote by doing synthetic division. When we get to an example, we'll see exactly what I mean by that. Now, if it's neither bottom heavy nor top heavy, n equals m, so they're the same degree, that means both are in a stalemate. So if they're in a stalemate, they're not going to 0, they're not going to infinity, they're going somewhere between 0 and infinity. So in other words, some finite number. And that finite number is going to simply be the ratio of those leading coefficients. So since they are going to a specific number, they are leveling off. That means there's going to be a horizontal asymptote at y equals the ratio of those leading coefficients. And if there's a horizontal, then there cannot be a slant. So there are two situations where we have horizontal, if it's bottom heavy or if it's the same. If it's top heavy, there's no horizontal, it's a slant. We find that slant by doing synthetic division. And my inappropriate shortcut for remembering this, bottom heavy, always makes me think of Jennifer Lopez. If you don't know what I'm talking about, it's best that I not explain myself. But bottom heavy, I think of Jennifer Lopez, otherwise known as J-Lo. J-Lo, O. If it's bottom heavy, it's J-Lo, it's y equals 0. Top heavy, on the other hand, you can think of Dolly Parton, Pam Anderson, although not so much anymore. When you're top heavy, you tend to lean over a bit because there's just too much weight on top. So you're leaning over a bit, you are slanted. Probably top heavy because you are fake. You are not real, you are synthetic. So if you're top heavy, you have a slant asymptote, use synthetic division. Sorry, no tricks for this guy. So here's an example. Let's identify our horizontal and slant asymptotes. Now I always love doing these questions because they're so much easier. I don't have to do what I did with all of the vertical domain restrictions. I don't have to factor anything out because it really comes down to these leading terms. 7x minus 2, x minus 1 might as well not even be there. They are irrelevant. Horizontal and slant asymptotes are found simply by looking at the original function, just the leading terms. I'll always start by looking at the degree. I see that the degree is the same, therefore I have a horizontal asymptote at the ratio of the leading coefficients. So I have a horizontal asymptote at 3/2, and since I have a horizontal, that means there is no slant. So here's another one. Why don't you try this one on your own? Hit play when you're ready. Alright, so hopefully again you looked at your leading terms. That minus 1 is not the leading term on the bottom, so it really doesn't matter. We've got 2x squared and x cubed. So I look at my degree, 2 and 3. This time we have a function that's bottom heavy. Anytime it's bottom heavy, I don't have to do any more work whatsoever. I'm just going to write down the answer. Bottom heavy means we have a horizontal asymptote at y equals 0. And since we have a horizontal, there is no slant. End of story. Now let's look at this one. Let's do this one together since this one's going to be slightly different. Again, still looking for horizontal and slant asymptotes, but this time I've got second degree on the top, and on the bottom I have a first degree. If I look at those relative degrees, I have a top-heavy function. So this time I know because it's top-heavy there is not going to be a horizontal, there's going to be a slant. How do we find that slant? Well, we use synthetic division. In other words, we simplify this fraction by dividing it out. So just like we did in a couple of sections ago, let's do our synthetic division. We're going to divide out x minus 2, which means we're going to divide out positive 2. Our coefficients on the top are 3, 7, and 2. Apply our synthetic. 3 times 2 is 6. Add together I get 13. Multiply I get 26. Add I get 28. That 28 represents the remainder. So the original function, 3x squared plus 7x plus 2 over x minus 2, is actually equivalent to 3x plus 13 plus 28 over x minus 2. Now, this is not my slant asymptote. This is equivalent to the original function. To get the slant asymptote, all you have to do is completely ignore the remainder and just take the proper quotient. 3x plus 13 is my slant asymptote. So we use synthetic division, but you actually don't have to do all of synthetic division. Just do enough synthetic division to figure out the quotient. You can ignore the remainder. If I throw the remainder in there, it's no longer an asymptote. It's the actual function itself. Ignore the remainder. The slant asymptote is the quotient. Here's another one. Hit play when you're ready. So once again, we've got 3 and 2, so it's a top-heavy function, which means there is no horizontal, it's just a slant. We figure out that slant by doing synthetic division. On the bottom, I've got x squared minus 4. I have two roots, positive and negative 2, so I'm going to have to do my synthetic division twice. So it doesn't matter which one I start with. I'll start with positive 2 and then do negative 2 second. On the top, I just have a single term x cubed. So that means I have a bunch of missing terms. If it's cubic, that means there should be at most 4 terms. So I'm going to put a 1 with 3 zeros. 1 is x cubed plus 0x squared plus 0x plus 0. Go through my synthetic, and I end up with a remainder of 8. But remember, I'm not done. I still have a second factor to divide out. The negative 2 needs to be divided out, so let's do that. And this time, remember, the 8 was the remainder on the first division. On the second division, it actually has two remainders. I've got 0 and 4. But remember, the remainders are irrelevant anyway. I started with a cubic, I divided by a quadratic, I end with a linear. So technically I have y equals 1x plus 0. Everything else is remainder. I don't need any of this. I only need these first two numbers. Really, I only need the first one because the second one is 0. So my slant asymptote is y equals x. So in the past when we did these double levels of synthetic, we always had problems that came up with remainders of 0 every time because within the scope of this course, we didn't need anything more complex than these non-zero remainders that we have here. But because we're just looking for a slant asymptote, I really don't care what's going on over here. I only need enough terms to write my quotient. Alright, so now we have all the steps necessary to analyze. Let's put it together in order to graph a rational function. So step 1 to analyzing the function is finding all the relevant information: domain, vertical asymptote, holes, horizontal slant asymptotes, x-intercepts, and y-intercepts. Remember that you find domain, vertical asymptotes, holes, and x-intercepts by factoring everything out. Domain are the roots of the denominator. Holes are what cancels. Vertical asymptote is what doesn't cancel on the bottom. X-intercepts is what doesn't cancel on the top. You can find horizontal and slant asymptote by assessing the degree. We don't need the factored version, we just need the degree itself. If it's bottom heavy or the same, we have y equals 0 for bottom heavy, ratio of the leading coefficients for the same. If it's top heavy, we just use synthetic division. And then of course y-intercept is just the ratio of the constant terms. Once we have all the analysis done, once we have all the information we need, we can go ahead and graph it. And if the information given isn't sufficient to be able to connect the dots, we can plot points as needed for direction. Now, technically, there is a leading coefficient test for rational functions, but unfortunately, that leading coefficient isn't always as obvious. And in order to apply that leading coefficient test correctly, we may have to simplify further, and thus maybe if you're not sure of the direction the graph is going, whether it's going up or down, just pick a random point, plug it in, and see whether it comes out positive or negative. So I've got 4 problems set up for us to do. Let's look at the first one together. So we want to analyze the function and then graph it. 5x over x squared minus 1. To analyze it, I'm going to list all my information out off to the side, and then I'll take all that information and plot it on the graph. Starting with domain. Now in order to get domain, we need to factor this out. There's only one thing to factor: the bottom, x plus 1, x minus 1. So we have domain restrictions at positive, negative 1. We can look to see if anything cancels. I see that nothing cancels, therefore there are no holes. Since there are no holes, both of those domain restrictions must be asymptotes. We have 2 vertical asymptotes on this one at positive 1 and negative 1. Now since nothing canceled, everything on the bottom represented a vertical asymptote. Any roots on the top represent x-intercepts. So since there is a root on the top, x can equal 0, we have an x-intercept at x equals 0. Next, I'll assess the horizontal and slant not by looking at the factored form but the original form. I see first degree over second degree. This is bottom heavy. Since it's bottom heavy, I know I have a horizontal asymptote at y equals 0. Since I have a horizontal, there is no slant. And then finally the y-intercept. Let's just look at the ratio of the constants. On top, the constant is 0. 0 over anything is still going to be 0. So I have a y-intercept at 0, 0, which makes sense because I have an x-intercept at 0, 0. So I have all the information I need. Let's go ahead and put it in the graph. So with polynomials, I would go ahead and plot all of the x and y intercepts. I'm going to do the same thing with rational functions. I'm going to plot x and y intercepts, but I'm also going to go ahead and draw in all of my asymptotes and my holes. So let's do that. We have asymptotes at positive and negative 1, vertical asymptotes at positive and negative 1. We have a horizontal asymptote at y equals 0. We have an x-intercept at 0. We also have that same point representing our y-intercept. This graph did not have any holes, so this is it. This is all I have to work with in order to graph my function. Now I just need to think about some prior knowledge. What do rational functions look like? Well, rational functions look like reciprocal functions. In other words, they can't touch this graph. So what I'm going to have, I have to have something, some graph, some nice smooth curve that approaches the asymptotes. So if I start to the right of x equals 1, I've got a horizontal asymptote and I've got a vertical asymptote. So basically I've got 2 options. The graph either needs to curve up here in the top right, or it needs to curve down here in the bottom right. So that's one of two options. It's either going to curve up here like this, or it's going to curve down here like this. Now, instead of wasting time with any leading coefficients, I'm just going to pick a random number, plug it into the original function, and see which one it actually is. Doesn't matter what number you plug in. You can plug in x equals 2, plug in x equals 3, plug in x equals 4, 5, 6, 7. You could plug in x equals 1,000,000. All that matters is the answer going to come out positive or negative? Because if it comes out positive, then I know my graph is up here. If it comes out negative, I know my graph is down here. So if I think back to the original function, 5x over x squared minus 1, plug in any random number you want. Plug in 50 billion. 50 billion times 5 is a positive number. 50 billion squared is also a positive number. Subtract 1, it's still positive. A positive divided by a positive is positive. So I know on the right side of x equals 1, I have a graph that's positive, always positive. So it's going to curve up here like this. Now from here, just like we did with polynomials, I like to use the concept of multiplicity to figure out what's going to come after it. I start on the right side and I work from right to left, and I'm going to use multiplicity to identify direction on everything else. So x equals 1, my asymptote. Now, as far as multiplicity goes, we typically only apply multiplicity to zeros, but an asymptote also has multiplicity. X equals 1 was my asymptote. It appeared only one time. So you can think of x equals 1 as having a multiplicity of 1. X equals 0 had a multiplicity of 1. X equals negative 1 had a multiplicity of 1. So basically, I'm going to cross that asymptote, or another way of thinking about it is I'm going to change direction every time I cross an asymptote or a 0. So if I'm going up on the right side of x equals 1, since I need to cross, I need to be going down on the other side. So that means my graph is going to be down here on the left side of x equals negative 1. Now I could also figure this out simply by plugging in a number. Between 0 and 1, I could plug in 1/2, and you'd end up with a negative number. Now the graph is going to be down here on the on the left side of x equals negative 1, but as it intersects at x equals 0, we have a multiplicity of 1, so it's got to cross straight through. So I can say between these two asymptotes, I'm going to have a curve that looks like this. I started out positive on the right side. I'm going to cross x equals negative 1, and I'm going to be negative. At 0, I'm going to cross again straight through, back to positive. At x equals negative 1, multiplicity was 1 again, so I'm going to cross again. Instead of being up here, I'm going to be down here. So I went positive, negative, positive, negative. I alternated. Every time I crossed an asymptote or a 0, each one had a multiplicity of 1, so I just changed sign. Positive to negative to positive to negative. Again, if you aren't confident with that, just plug in points. Just pick points. Pick any number bigger than 1 to figure out the graph is positive. Pick a number between 0 and 1 to figure out the graph is negative. Between negative 1 and 0, the graph is going to come out positive. To the left of negative 1, your graph is going to come out negative. Alright, here's another one. Hit play when you're ready. So we're going to identify everything, starting with domain, so we've got to factor everything out. On the top, I can factor out 4x. On the bottom, it's going to factor the same way it did before. So I have two domain restrictions again, positive, negative 1. This time, though, the negative 1s cancel out. Therefore, x equals 1 is a hole. Now I'm going to find the location of that hole, the y value of that hole, by taking 1 and plugging it into what remains. 4 times 1 over 1 plus 1, that's just going to be 2. I have a hole at the coordinate 1, 2. So the x plus 1 remained on the bottom, so we have a vertical asymptote at negative 1. 4x remained on the top, so we have a x-intercept at x equals 0. Going back to the original, the degrees are the same, so my ratio of the coefficients represents my horizontal asymptote, 4 to 1, so y equals 4, no slant asymptote. And since I have an x-intercept at 0, I can say that I have a y-intercept at the same spot, also because the constant term on the top is 0. So here's all the information I need. Let's go ahead and plot it. Once again, vertical asymptote at negative 1, horizontal asymptote at y equals 4. I also had some intercepts. I had my x and y intercept both at 0, and I had a hole located at 1, 2. So I'm going to go ahead and put a dot right there at 1, 2. Now from here, I could say let's plot some points to figure out direction, but I don't need to plot points because I've got 2 points right here to help me out with direction. The fact that my coordinate is right here and my hole is right here means out of my 2 options, whether the curve being up here or down below, clearly the curve has to be down below. It has to intersect those two values. So here's going to be the curve on the right side of -1. To get the curve on the left side, again, I've got two options. It's either be curving up here or it's going to be curving down here. But I only have one x-intercept. I can't make new x-intercepts now that I'm graphing. The only time the graph crosses the x-axis is right here. Therefore, it does not cross the x-axis anywhere over here. If the curve was to be down here, it would have to cross the x-axis, but it's not allowed to cross the x-axis because there's no x-intercepts. Therefore, the curve must be up here. I can also confirm that because of multiplicity. X equals -1 appeared only once, so if I'm going down on the right side, it must be going up on the left side. Alright, here's another one. Hit play when you're ready. So once again, we'll factor everything out. The top is going to be x plus 3x plus 1. So I only have one domain restriction, -2. It does not cancel, so it's not a hole. It is a vertical asymptote. And I have two remaining factors on the top, so I have two x-intercepts at -3 and -1. I can find horizontal and slant by looking at the original. This time I have a top-heavy function. Since I have a top-heavy function, it's not horizontal, it's going to be slant. I'm going to find that slant by doing synthetic division. Drop the 1 times -2, add it, multiply, and add. I get a remainder of -1, but I really don't care about it. I only care about the 1 and the 2. So I have a slant asymptote at y equals 1x plus 2. Find my y-intercept by looking at the constant terms, 3 over 2, so 0, 3/2. Let's go ahead and put all that in the graph. Vertical asymptote at -2. I had a slant asymptote at y equals x plus 2, so I just graphed the line y equals x plus 2, y-intercept at 2, slope of 1, but it's an asymptote. I draw it as a dotted line. I also had some x-intercepts, -1 and -3, and a y-intercept at 1.5, in other words 3/2. I did not have any holes on this graph. So this is the information I have. So since I know the graph has to approach the asymptote, and I know I've got points right here and right here, I can go ahead and basically connect these two dots, but keep going so that I have a curve that approaches the asymptote and connects those 2 points. Now I know I can't have any curve up here because that would violate my vertical line test and thus would not be a function. So if I look on the left side of x equals -2, it's either going to be up here or down here. Well, since we clearly have an x-intercept, it must be up here. Now hopefully you can kind of see that same hammer time graph, that reciprocal function graph, where the curve is in the top left and the bottom right. Instead of the asymptote being horizontal, the asymptote is slanted, so it's just kind of stretched diagonally. And again, at any point, if you feel you're not confident about where the graph is going, just start plotting random points. And the last one, go ahead and give this a try. Hit play when you're ready. Alright, so let's factor everything out. The bottom should be straightforward, x plus 2, x minus 2. On the top, it may take a little bit more effort, but it should come out to 2x minus 5 and x plus 2. So my domain restrictions are positive, -2. I see that x plus 2 cancels out, so -2 must be a hole. I can figure out the location of that hole by plugging into what remains. When I plug it into what remains, I get 9/4. 9/4, when I plot that, it's just going to be 2 1/4. So -2 was a hole, that means positive 2 was an asymptote, and positive 5/2 is my x-intercept. The degrees are the same, so I'm going to have a horizontal asymptote at y equals 2 with no slant asymptote. Looking at the constant terms, 10 over 4, I have a y-intercept at 5/2, or 2.5. Let's sprinkle in all the information that we've discovered. We've got vertical at x equals 2, horizontal at y equals 2. We have a single x-intercept at about 2.5, and our y-intercept is at 2.5 as well. We also had a hole. Let's not forget about the hole. It was at -2, 2 1/4. So there I can hopefully clearly see the direction of the curve. I'm going to have one curve down here and the other curve up top. Now hopefully it's clear that this is going to take a lot of practice on your part. Luckily I've offered you plenty of practice, available not only in your homework but also the extra practice worksheet available on the daily agenda. So make sure you are practicing. If you practice enough, it's really easy to get the hang of.